Good morning. Welcome to Krishna's classroom. We continue with our explorations of differentiability and the stature of the fundamental theorem of calculus in the light of what is called the measure and integration theory. With this objective, of course, we have explored already the monotonically increasing functions, and we have found that it is almost everywhere differentiable, that is, the derivative exists almost everywhere. This we did by introducing the upper derivative and the lower derivative, and upper derivative and lower derivative are defined everywhere, but their equality happens everywhere except at a set of measure 0, and the monotonicity is the essential criteria for this. Okay. Now we want to go beyond this, but before that we look at or construct some more tools with the objective of looking at the fundamental theorem of calculus. So we introduce two functions, namely the divided difference function and the average value function. So let us define them first. Definition. First, we define what is called the divided difference function, and then we introduce the average value function. So let over the closed bounded interval A. We are taking a closed bounded interval. Now extend f to the right by defining fb for every x belonging to b plus 1. So now it is defined on the interval a to b plus 1, so that we can comfortably define all these two functions. For less than or equal to 1, define the divided difference function f by h. Now this is well defined because you can see that since h we are considering to lie between 0 and 1, you see that f of x plus h at the extreme end b does not spill over b plus 1, and we have extended the function f beyond b to the interval b to b plus 1 by taking fx equal to f of b. Therefore, this is well defined. Okay. Likewise, now the next definition. This is called the average value function. This is the average value. Under the same conditions, f we define one by h integral x to x plus h. Now this is for now you see that everything is well defined. X plus h belongs to b plus 1, which is positive. Then this is what. Okay, fine. Now these are well defined. Now we prove the following. That is integral u to v difference hf, this is equal to average h at v minus where of course a now this is the result that we first established. It's simple computation using the definition and probably a change of variable in the integral. So let us first give the details of that. After that, we give an estimate on the of the integral of the derivative of f. This is for what are called monotone functions. So let us first verify this result. Okay. So let me just do that. Okay. So let us first prove this result. Okay. So we compute this integral u to v this is equal to, see, we use this h and then let us work this out with in the following way. So we can write this as integral u to u plus h f of divided by h plus integral u plus h to h plus h f of now here of course you have u plus nh is, see, even when u becomes b, you see that this is uh, sorry, even when u plus n minus 1 h equal to v, we will see that u plus nh is in from b to b plus 1. I mean, that is the way it would possibly exceed. Now what you do is you can rewrite this as with a lot of cancellation techniques. Okay. So you have got this term coming there with a minus sign, and this term, the same term appearing here, they cancel out and so on. And because it's with a change of variable, they will cancel out and so on. So we will work it out. So you have this equal to minus integral u to u plus h integral NH u plus NH divided by H. Now you see that u plus n minus 1 it may just exceed this, that's all. So that you have f u plus therefore integral u to v divided difference of a over the interval ab over the interval u to v, this is equal to minus 1 by h integral and that's equal to that proves this result. And this result we shall use. Okay. So now we can give an estimate of, so we now give an estimate of f derivative. Of the integral of f derivative on AB for monotone functions. Here we observe the following. If you are taking a monotone function, say specifically an increasing function, then you see that the function is differentiable almost everywhere on the interval A2. Therefore, f derivative exists almost everywhere except possibly on a set of measure 0. Okay. Now, we want to give an estimate of this integral, this derivative, the integral of this derivative. So, this is what is stated in the following problem. Let function on the closed bounded interval then you know that f dash exists almost everywhere on the interval. Then f derivative is integrable over AB, and we have an estimate of this integral. This will give a bound for this integral in terms of the value that f takes at A and B. And is bounded by so this is an important estimate. Yeah. In fact, later on we will be looking at where this is going to be. These are for what functions you have equality of this. Okay. So let us prove this result. Remember how we have defined on B, extended the function from B to B plus 1 as the constant value fb. Okay. Therefore, it is an increasing function on the interval A to B plus 1. Then f is measurable and therefore, which implies the divided difference functions are measurable. Now, by Lebesgue theorem, f is differentiable almost every. Almost every. AB. Now we choose H equal to 1 by where n is a positive integer. Then look at this function. Difference, the divided difference with 1 by n of f. Is a sequence of functions is a sequence of non-negative measurable functions. Look at the definition of this divided difference, which point-wise converges to point-wise point-wise almost everywhere. Almost everywhere. That means the failure is only on a set of measures 0. F derivative, because we know that F derivative exists almost everywhere, and you see that this tells that almost everywhere it point-wise converges to F derivative. Now we apply Fato's lemma. By Fato's lemma, we have integral a to b f derivative is less than or equal to dim inf of h, of course, going to 0. Okay, right? One by n. Now, what we have is this. By the change of variable formula, for each natural number n, since f is increasing, it's an increasing function, we have integral a to b divided difference function by n. This is equal to 1 by n integral b to b plus 1 by n f minus and that's equal to fb minus 1 upon 1 by n integral a to now this of course is less than or equal to f of b minus f of a, since f is increasing. F is an increasing function, therefore this is equal to this. Okay. Now you have therefore limit supremum n tending to infinity of one by nf is less than or equal to, that means you take this inequality, this I have here inequality, okay, this is equal to, okay, this inequality, take this inequality and you take the limit supremum of this integral. Therefore, we have the following: integral a to b f derivative is less than or equal to limit infimum that comes out from the Fato's lemma this, and that is less than or equal to limit supremum of one by n and this of course we have just now estimated as less than or equal to fb minus that is less than. So that completes the proof of this lemma. Now we make a few remarks. Okay, so that completes the proof. Now we observe that the right hand side of the above inequality is valid for the extension of f on the open bounded interval AB to its closure. Fine. To its closure in the sense that by maintaining the monotonicity. Okay. By that is clear because FB is the value of F at B. It may be replaced by any higher value and this may be replaced by any lower value as, or we are attributing now values to F at A and B and keeping the function monotonically increasing means that it is valid for any value other than the original FA or FB that is known, because we are extending to the two endpoints, namely A and B. So at A it can take any lower value. At B it can take any upper value. So essentially it does not depend on the estimate on F, on the values of F, that's one remark that we want to. Therefore, a much better estimate would be this integral A to B f derivative is less than or equal to supremum of and minus infimum of x belonging to AB Now this is probably a more tighter estimate that you can have, because you replace FB by the supremum of Fx on the interval A to B and Fa by the infimum of Fx on the interval A to B. And now we are considering a monotonically increasing function. Remember that. So that is one remark. Another remark, okay, a consequence of this we can immediately say. So if F is continuous, at the endpoints A and B, then we have integral A to B f derivative fb minus and conversely if A to B f derivative then f is continuous at the endpoints. Now we make another remark. So this is the first remark that we make. The second remark is that even if f is increasing and continuous, continuous. At the endpoints, on AB, the inequality may be a strict inequality. Now we give an example. Consider the Cantor-Lebesgue function involving the Cantor set, and you see it's a sort of step function which goes from 0 to all the way to 1. I think we have discussed in detail, or you just look into it. Zero, 1. Now, f this is equal to 1, whereas we have phi derivative equal to 0 almost everywhere. And that implies integral a to b, this is equal to 0, which is strictly less than 1, which is equal to, so strict inequality holds in this case. Now this is a very interesting observation. Okay, so even if continuity is there, you cannot assume the equality in all cases. There are situations where it would fail to. Oh, of course, that means, so the question is, equality. Now this is the question that automatically comes up from. So you need possibly some more conditions on F. Now we shall prove that the equality holds. So what we will prove later is that the equality if and only if, that's a nice characterization theorem that we are going to prove. F is what is called absolutely continuous F is absolutely continuous on we have not introduced this term so far, but this question you note, okay, and this is what we are going to do, and we have to do a lot of groundwork to establish this result, and that's a beautiful result. It simply talks about the integral a to b f derivative equal to fb minus fa. That is essentially the what is called the fundamental theorem of calculus. Okay. So when is the fundamental theorem of calculus holds? Now you see that this much condition is not enough to guarantee this. Okay. So here you can get only an upper estimate, and the equality would hold only if some further conditions are imposed on the function, and this is essentially what is called the concept of absolute continuity of the function f. Now we also make another observation. In the absence of such a function, such a situation, we will have the result failing to hold. Okay, so let us take this. So we have another third remark. In the absence of the condition that f is increasing the inequality fails to hold. For instance, you look at this function. Consider f of x defined as x square sine 1 by x square for x equal to 0. Consider this function. Now this function, you can work out the f derivative. F derivative exists at x equal to 0. That's easy to see. At x equal to 0, it exists. And you see that f derivative is defined on that means at all points on 0, 1. But you see that f derivative is not continuous. You see, f derivative is not continuous on at 1. See, limit exists. And if you compute the derivative, see f derivative of x would have the following components. What is it? It's on the interval, this one. Now, f derivative of x equal to 2x square minus x to the power minus 2 x to the power minus 3 x cubed. Therefore, this is equal to 1 by x plus x square and 0 is differentiable everywhere. But you see that f derivative of x on 0. That is because of this function. Okay. See, what happens is that you have a very rapid, although this, see, the function is of this type. This is x square, this is minus x square, and this function is something that oscillates between these two branches of this. This is a rapid oscillation here. Now you see that the function is certainly continuous because this x square dominates over this. Now if you compute the derivative at x equal to 0, it is going to be fx divided by x limit x tends to 0, and you see that because of that x and x cancels here when x not equal to 0. So you get x sine 1 by x square is coming, and that goes to 0. Okay. So the derivative computed at x equal to 0 is 0. Okay. So the derivative exists, but the derivative is not continuous because this function is something that does not go to 0. Okay. In fact, you see that this part, the limit of this as x tends to 0 does not exist. That is the problem that you. Okay. So the why it is happening is that the function that you have taken is not something that is an increasing function, but it oscillates. It's an oscillating function. Therefore, you cannot do away with the restriction that f is increasing. So this is the third remark. Okay. Now with this, we leave today, and then we go on to consider what are called the functions of bounded variation and slowly converging to the absolutely continuous functions defined on the interval. Okay. Right. So we are slowly going over to that class of functions and eventually prove the theorem, the equality in this problem for such functions. Okay, thank you very much.